Good morning, everybody. Hopefully you can hear me and also see the screen. I'll bring up my video for a moment. Okay. Scott, do you want to bring up your video for a moment?
Yep.
Yeah, there we go. Okay, well, welcome and thank you for joining us this morning or this evening for a lot of you, or in the middle of the night for some of you. We will be talking to you a little bit about battery emergencies today. And obviously this is a hot topic for a lot of people, and this is a little bit different take on the battery emergencies, because what we're not focusing on is how do you put out the fire with a lot of the lithium ion batteries. But what we will be focusing on is when we have all of these different batteries in mixed loads and things, and we know that one has a problem, how do we use detection to figure out where that problem is and what can we do about that? And so we're going to spend this time walking you through that. As with all of the webinars and things that we do, this is being recorded and we will have it available to you after the recording, after it's all done. So I'll pass it over to Scott to say hello and go from there.
Hi there, welcome everyone. Again, the main purpose of these webinars we're doing is to provide educational resources to people. We obviously are focusing a little bit on the chemistry today, so this will be a more chemistry heavy presentation, but we will also be hitting on some of the response aspects as it pertains to detection capability and how to use detectors to help you out to respond to those.
Okay, so we'll get started. I'm going to turn off my video and let you guys just see the screen now. Okay, so we're going to start off just with an introduction to the Proengin Academy. And as Scott said, Proengin sponsors this series of webinars, and it's mainly for them to provide an educational opportunity to their users and potential users out there. You can, as always, gather information from the Proengin team, and they will be sending out follow-up emails with links to the video, as well as white papers and things that relate to this topic. So a great way for you to gather more information. And as always, a lot of our users can't join us during the actual time, so that gives them that replayability. So the way we have it divided out today is just to talk a little bit about battery emergencies and why are we here and what is our role, a background on some of the battery types, and then the hazards associated with each of those types, detection from off-gassing, and a little bit on the different detection technologies. As with all webinars that we do, we are kind of product agnostic. Obviously, we will show the Proengin products, but there is no one solution out there that will meet all of our needs. Therefore, we'll show several other products that will help with this. And then some tactical considerations at the end and a little bit of a review. So with that, I'm going to start out with some battery emergencies. And I like to show this video here just because I have no idea what they're saying in it, but to show you the speed at which things can change. So as we all know, battery emergencies are quickly becoming one of the largest hazardous materials incidents out there today. And the number of deaths and things that have occurred because of this rapidly evolving trend is problematic. So I'm gonna turn the sound off so we don't hear what it's saying. But if you start looking at this scooter going off and you see what looks like smoke coming out, just remember that's the toxic gases, that's not smoke. There is no flame yet. Once we get to the point where those toxic gases start reaching the flammable point and then the temperature starts to exceed, all of a sudden you'll go away for a moment and you'll come back, and as these toxic gases are now going to come ignite. And so they've just ignited, so they pan back. Now you start to see what's happening. Now, if you start looking at this fireball, you'll see every now and then the jet fires coming out the sides. That's what's happening every time a battery releases the gases that are pressurized inside. So as it continues to heat up, you're going to pressurize the material inside. You're going to change a lot of these to the gas state from the temperature. And then as it reaches that pressure, it's going to release the valve and it's going to shoot out the side all of the different gases. Unfortunately, this is where a lot of the problem comes in. People start thinking that it's just smoke, which you see now. But reality is, in many cases, it's the gases that are very toxic that are coming in. So now this is really easy because we're just talking about a scooter. But what happens as we get bigger in scale and we have more of the toxicity coming up? So this was just an electric bus fire. And in this case, the batteries are on the top. But now we actually have a problem because a lot of the gases are heavier than air. So as these gases come down, what happens to the ability to escape to the people that were inside the bus if they weren't able to get out quickly? And so we have a lot of problems there. And then, of course, let's go even bigger and let's go to a factory fire. And what happened here with all of these batteries going off is there was information provided out to the community that the fumes weren't toxic. Well, unfortunately, as a lot of these gases escape, they are toxic. And we're going to get into that a little bit more. But as we start looking at all of this, just remember, when we start out with these small one battery incidents, that's not as tragic as what happens as we get more and more of the batteries involved. Now, one of the big problems we have is not every battery is the same. And there are a variety of different batteries out there today. Every one of them has its own hazards collection. So starting out, there's a few different definitions we got to start out with. So first, what is a battery? So just remember, a battery is always stored energy. So the issue that we have there is that it's going to convert chemical energy to electrical energy. And each one has a different chemistry. Those chemistries will help decide what its energy density is, the size and weight of it, the voltage it produces. All of those things are what's competing and why we have such an evolving change in the science behind batteries. The big issue is everybody wants a battery that's smaller and lighter, but provides more power longer and without the problems of losing its capability over time. So when you start cycling it, that you don't lose the high end. So everybody's trying to compete for that perfect battery. And unfortunately, that's going to be something that goes forever. As we get closer and closer to that perfect battery, and you have that high energy density, the problem is going to be that we're going to have more and more energy in a small space. Now, how are they all designed? Well, there's several different looks to batteries. They can be squares, prisms, they can be these flat packs, they can be the cylindrical cells, but it doesn't really matter what they're shaped like. Every one of them has a few different things to compare. You've got the anode or the negative electrode, the cathode or positive electrode. Those generally have different materials of interest. So a lot of those have things like lithium metal might be one of the incidents. The electrolyte, the material in the middle through which the electrical current is going to pass. That is oftentimes a hydroxide with some of the batteries. And so this is where you have these chemistries that are coming up and are affecting us. And then of course there's a separator. That separator is keeping the material from short circuiting. And when we think about that, it's just an insulator. As we get to smaller and smaller systems, that insulator also gets smaller and smaller and thinner and thinner. And when you think about it and you compare it to a plastic wrap or saran wrap or whatever you want to call that, this separator right now is smaller and thinner than a piece of saran wrap. So a slight insult to the outside of a battery is enough to cause the short circuit, which in turn will cause the battery to start to fail. And that's where we start to see these gases being produced. Now, the hazards that we're generally looking at, we've obviously got our shock hazards. So as we have voltage in a small space, we are going to have the DC energy and any arcing that could come with it. We're also going to have the chemical hazards. So those electrolytes that are in the battery, many of them are corrosive and others are toxic as we get to the newer ones. A lot of these will off-gas when they're operating normally. It may off-gas other materials when they're operating abnormally. And that's where we're going to get into figuring out what's going on with these. And then, of course, you saw that a moment ago, but the fire and explosion hazards. When these things are under pressure and the temperature or something is changing inside, they're going to liberate the gases. How much is going to depend upon the size of the battery and the type of the battery. Now, most importantly, what do we have to talk about Well, anything that's over 50 volts is going to be considered hazardous. How do we get to that 50 volts when we're talking about a lot of these small batteries? Well, it's the way they're connected. So when we start looking at how much voltage is there and what we have to think about, uh, you'll see a lot of the scooters and things are 48-volt devices. And that's intentionally to stay below this hazardous component level. But when we start looking at all these batteries, they're connected together. So an individual battery may be pretty small and not something that we worry about. But as we start building those into modules and those modules into packs, you start getting all of these things connected together to increase their voltage and increase their current. And that will allow them to last longer and provide more power. So when we have to look at the way they're connected, when they're connected in parallel, so when you have black to black or red to red or just positive to positive, negative to negative, that increases the length of time that they work. So if I had a flashlight, that would mean that the flashlight, instead of working for 2 hours, might work for 4 hours. But if I connect them in series, red to black, black to red, hot positive to negative, negative to positive, when I have it in series, that is actually going to increase the voltage. That's going to give me the brighter flashlight. It's not going to last longer. It's probably going to say that same 2 hours, but I'm going to get a lot more brightness out of it. And so those are the ways that we connect these. As we start looking at those, the ones that worry me the most are the ones that are connected in series, because that voltage continues to increase. And as long as all those connectors are in place, we have to start counting up how much voltage is really there. So if we're looking at a battery that's got 3 volts, but there are 100 of them in series, now we're at 300 volts. And that puts me well above where I have to worry about a hazard from electricity. So where do we go from here? There are a ton of different battery chemistries. And we've used batteries. I mean, batteries have been around since 1800. It's really only the last 100 years that we've seen such a vast increase in the speed at which batteries have been developed. But when we think about the lead acid battery that we use so much still today, that was developed in 1859. And that was our first rechargeable battery. So looking at that one, we have 2 different types of batteries. We hear the terms primary and secondary. Now, why didn't just call it non-rechargeable and rechargeable? I don't know. But in terms of primary, those are our regular alkaline batteries or the lithium metal batteries. Those are not rechargeable. There are a couple of rechargeable lithium metal batteries on the market, but most of those are in the military marketplace today. There are some being researched though. Secondary batteries are the rechargeable batteries. You usually find the lead acid dry, the nickel metal hydrides, the nickel cadmium batteries, and then of course the lithium ions, the ones that have brought batteries to the forefront of everybody's mind today from an operational perspective. So let's look at each of these and just see where the hazards exist. So an alkaline battery is probably the one that we all did our first neutralization experiment with. And when I say that, it's about how many times we forgot the batteries in, I'll go old school here and say our old Walkmans or our original cameras, and we left the batteries in it. And we went to open up and start checking to put the batteries in, forgetting that we had left them in there. We open it up and there was all this corrosion there. And so I know as a child, we would take like a Q-tip or a cotton swab, and we would put a little bit of soda or like Coca-Cola on it and use that little bit of acid to neutralize the material that was there, the corrosion. Not knowing at the time that that was our first neutralization experiment. And what we were doing was neutralizing the material that had built up, the hydroxides, and getting this system ready to use again. Now, that brings to mind then that we have a hydroxide issue. There is up to 20 milliliters of a very strong hydroxide, whether it be generally potassium hydroxide, but sometimes it can be sodium hydroxide, inside that battery. So if that battery decides to swell and release its material, it's going to be a hydroxide. Yet generally when they release it, it's coming out slowly as a liquid, but it can also come out under pressure as an aerosol. Now, we also, at one point, were not allowed to throw these away. These today are thrown in the regular household trash. Personally, I always cover the connections with tape before I throw any battery away. And I usually save them all and bring them to the landfill so that they can take care of properly. But originally, there were toxic mercury oxide connections inside of there and the electrodes. And so that was why we originally saved all of these, because they had mercury in there and you didn't want to dispose of them as household waste. Most today do not have that, but if you come across some old batteries, they may very likely have the mercuric oxide in there. Most of them today are the manganese dioxide. Still, do we want to throw them in household waste? I'm a firm believer that we don't, but it is allowable in many places. So the hazards here are generally, but depending upon which electrodes are inside there, you also have all the toxicity hazards associated with this one. Now, lithium metal batteries, from my background, we saw these mostly in meth labs. So probably not the nicest place to find them, but these batteries are used still today. I see a lot of them used in watch batteries, key fobs, all those types of things. But one of the issues there was the long life. Now, in the meth labs, they would actually cut these and get the lithium strip out of there to use the water reactive metal in the actual cooking process. But what happens here is you literally have a strip of pure lithium metal inside of there. Now, if air, and even the humidity in air hits that lithium metal, it will spontaneously combust. So we end up with a real problem here that we have lithium metal inside of these. Now, reality is the bigger problems I've had with these batteries is these button batteries. And that's generally if a child swallows them. And the issue that you have is they will lodge in the throat and create a hydroxide-like reaction and will burn in pretty much corrosive burns inside the throat of a child. So issues that we have here is water reactivity. Remember, when one of these is on fire, in most cases, if it's a small lithium battery like these ones, then those ones, by the time they put the fire, they've had put water on the fire, because the first dew is going to see fire and put water on it, then you're going to actually use up all that lithium. It's pretty quick. And actually on planes and things, when they have a small device powered by a lithium metal battery, they still recommend using water because you use up all of the lithium very quickly. It gets hot, gets fast, but it'll get used up. It's when you get to lithium metal with larger fires that you've got to be really careful about not using water. Now, lead acid batteries are the ones that actually concern me more than most. And reality of this one is because of the toxic gases that they produce. Now, when you have a regular lead acid battery and it's working properly, it will release hydrogen and oxygen gas. So when you have let's say, I see this all the time because I live in Florida, a golf cart that somebody has a battery powered golf carts, and they store them in their garage here, and they have the doors all closed. And one of my neighbors kept having his carbon monoxide sensors going off in the house every night, yet they could never find a problem. Opened up all the garage doors, everything went down. And I asked him, I said, are you charging your golf cart in the garage while the door's closed? And he said, yeah. And I said, okay, well, that's probably your problem. You probably are producing hydrogen gas, which is lighter than air, which is filling up your attic space coming from the garage and setting off your CO sensors. And once they stopped charging the golf cart in the garage, everything went away. So reality was the CO sensor was giving them alarm, but it was alarming because it was cross sensitive to hydrogen gas. Now, if it wasn't working properly, then when you get the hydrogen sulfide gas. So this has happened many times where, especially in vehicles, we had an incident in Florida on the 75, Interstate 75, where a woman and her child were driving down the highway in a Porsche, and they had pulled over to the side of the road. And when the response units got there, they were dead in the car. And everybody assumed it was a hydrogen sulfide suicide. But reality was, they didn't pull to the side of the road casually. The car was still in drive. They had come from the dealership where the battery was overcharged. The battery was overcharged, releasing hydrogen sulfide inside the car because where the battery was located. The problem that ended up happening is, as most people do with hydrogen sulfide, they get used to the smell. And so the person put the windows back up because they didn't smell it anymore, and ended up having a toxic dose of hydrogen sulfide gas, killing the mother and the child in the vehicle. So the real problems with these, not only are the corrosivity and the fact that they can actually get pretty high temperature and can release the electrolyte as an aerosol, but also that they produce toxic and flammable gases as they operate. So the flammable gases is normal, the toxic gases is abnormal. Now, we did switch for a short period of time to nickel cadmium batteries, and they're still in use today. But the issue with the nickel cadmium batteries is they had that memory effect, and they also tended to be really heavy. So you see nickel cadmium batteries came in and they were used in a lot of cameras. And the issue that we had with that was they made the cameras really heavy. But the problem also was that you got those memory effects, and if you didn't cycle it properly, you would end up with a short life battery. The primary hazards with these, they had a corrosive electrolyte, but a lot of the problem was the cadmium toxicity. And so a lot of people were trying to get away from the use of cadmium. And from that went to the other metal hydrides. And what you ended up here was a corrosive electrolyte still, but they also produce hydrogen gas when they're overcharging. So in this case, unlike the acid batteries that produce hydrogen gas when they're normal operations, a nickel cadmium or nickel metal hydride will produce hydrogen gas during abnormal operations. And this is really important because these things will help tell you what status your batteries are in. Now, after the nickel metal hydride, we switched over to the lithium ion that we hear so much about today. And there are so many different types. The ones I see a lot are the lithium iron phosphate, or the LFP batteries. But we see more and more of these every day, and the chemistries are changing all the time. What happens with these, and why did everybody want to go to these? They have a long cycle life. They have high energy density, meaning they're really small, but they give us a ton of energy. Very few memory effects on them. They can sit there on a shelf and be perfectly fine. And they're relatively maintenance free, but they have problems associated with them. Most of these have a battery management system within either the charger, within the battery, and they talk to one another. So using a charger that's not necessarily for the right battery, so buying some, I often explain to people when they buy one from the 7-Eleven, instead of buying it from Apple for the Apple device, if you start feeling the tip of that battery cord after you've charged, you'll feel that it's really hot. And that's because you've overrode the battery management system, and you can actually start getting problems. Batteries that are lithium ion are generally shipped at no more than like 30% charged, but below 80%. And so they're generally in that range. And the reason behind that is that's when they're safest. When you get above 80%, you start to have more problems. And when you get down to really low levels, you start to have problems. And so it's always shipped in this mid range. And they chose that range based upon the most stable point for all of these batteries. Now, the thing that we've all seen now with the batteries, and you saw in those videos up front, is when you get a cell failure and those cells are in modules, those cells end up affecting all the cells around it. So you could have either a failure from manufacturing failure, a failure from a thermal insult, a failure from an external pressure insult. Any of those types of things can cause the battery to go bad. And as that battery starts to heat up, that's going to start to give all the other batteries around it a thermal insult. And as those batteries heat up, you're going to see that same thing happening throughout, and you're going to propagate that entire system through. And this is also why the problem is to cool these batteries. So when you start thinking of that, and you have that temperature that's coming out and touching all the way around it, these are all inside some type of casing. With that casing, if you can't get into the battery and you're actually putting water on that outside insulation part, you're not cooling these batteries enough to overcome that thermal runaway and propagation event. And that's where it comes down to over and over again, is that we see huge amounts of water being used because you're actually not accessing the battery, you're accessing the outer part, the shell, which has insulation, and so the cooling is really not getting to the batteries. Now, there's new chemistries being looked at all the time. I would say one of the ones that you'll see pretty soon is going to be those sodium ion batteries. So instead of lithium ion, seeing sodium ion. Going to have a lot similar types of issues. And then we're seeing some of the rechargeable lithium metal. That will have more issues with the water reactivity. So as we start getting more and more of these chemistry types, we'll have to keep following up with what are the tactics and techniques that we're going to use, not only for suppression incidents if they are involved in a fire, but also what are the gases that they give off and how do we detect those in near real time. So I'm going to turn it over to Scott for a moment and have Scott talk a little bit about the detection side of things, and then I'll come back on and talk more about how do we address all of this.
Thanks, Christina. So we talked about the different types of batteries, and so because of the nature of how they work and the materials that are inside there, as far as how they're using how they're generating the electricity from the chemical reaction, or how they're storing the energy from the chemical reaction, this is one of the key charts of the presentation today, hopefully. So there's two classes of things that are helpful to us as we work to identify that. So that is the normal, so what they will produce normally when they're operating properly. So as Christina talked about, for example, with the lead acid batteries, they produce both hydrogen and oxygen as part of their normal process. However, if they're operating abnormally, which is usually on some sort of thermal runaway event, or it's not behaving as it should, and it's giving you some of these warning factors. A lot of times these warning factors, by the time you get them, it's too late, unfortunately. Those are shown in the red. So for example, with the lead acid battery, if you're getting hydrogen sulfide, that is actually not a good situation for you to be dealing with them. But the important thing about this chart is the materials, and because we have the ability to measure some of these materials, and especially on a thermal runaway event, it becomes important for us to allow us to identify those materials. Or if we know the opposite side of it, if we know that, like for example, you're having a wet lead acid battery that's in thermal runaway, you know what you need to be monitoring for as far as some of those harmful gases for that. So it allows us to use both identifying the class of materials that are present. It also lets us monitor the nature, know what to monitor and look for, especially if there are victims that are experiencing some of that chemical exposure that's a result of that. And as couple key things as we saw in some of the videos, a lot of times that chemical reaction that produces the harmful gases that potentially can take us out. And we'll talk a little bit more about what those concentrations are. Those will occur before the thermal runaway does. And those are a lot of times what can take us out pretty quickly with some of those materials. So we'll talk a little bit more about that, but the AP4C being one of those tools that you can utilize. And we're going to talk really over the next slide on a series of what sort of detectors we can use to help us identify and understand the nature of the risks and what we need to do from a response standpoint from there. So if you can go to the next slide, and then the next slide with it. So first, as far as detection standpoint, there's really 4 major things that we'll talk about that should be utilized for it. So that's your pH paper, your F paper, a CO sensor or electrochemical sensor, and then the AP4C. So the AP4C is helpful from the standpoint of it's very sensitive, but it also gives you indication on a variety of the chemical classes that would be seen from these. So from the standpoint of it can detect phosphorus, hydrogen, nitrogen bonds, hydrocarbons, arsenic, and sulfur. And those are, as we see with those chemistries, there's a number of different types of batteries that have the presence of these materials, and therefore it's a helpful tool to be able to do that. It's also giving you quantitative data as far as the nature of the concentration, and it's a very quick responding, and each channel is discrete and independent of one another from there. And then the other important point, which it doesn't really talked about a lot is some of these materials, if they are presenting themselves, they most likely could be presenting themselves as an aerosol threat. So it's solids that are then aerosolized into and behaving like a vapor. And so one of the challenges from a detection standpoint is a lot of detectors have filters on the upfront of them, and they preclude the ability of those detectors to then see those materials that are present. So that can sometimes even be more challenging. When you think your detector can detect something, it should be able to detect it, but if it's in an aerosol, it's not able to detect it. In the case of the pH and the F paper, that allows us to identify, it's letting us know, are we dealing with an alkaline threat, or are we dealing with an acidic type threat from the pH associated with it. So the acidic response that you get is indicative of the type of class or the major classes of materials with them. And then in the case of the F paper, it's also helping with libs and understanding that those are present. So we'll talk a little bit more about that. And then as well as understanding your CO sensor with it. So it's allowing you to know if hydrogen gas is being produced, which is important for that's normally done with, it's an out product of some of these materials with it. So it's letting you know there, as well as it can cause some other issues with it. And we'll talk a little bit more about the cross sensitivity kind of in the next couple channels. A slide, sorry. Next slide, please. So first, just a quick overview on flame spectroscopy for those of that you may not be familiar with it. It can be referred to as a variety of different names. Flame photometric detection. It's part of it's an atomic emission spectroscopy process. It's just using a flame as one of the subcomponents of that. So in the case of atomic emissions, you can use an energy source. So that energy source can be in the form of electricity, it could be an explosion, or it could be a flame. What you're trying to do is, in all cases, the incoming atoms, and when those atoms are excited and then they relax, certain elements produce an emissions, which you can then collect and analyze that. And each emission is specifically has a fingerprint associated with that element and that element only. So below, we're showing you the response of calcium, copper, and potassium. So our eyes intrinsically, because we can pick up the visible spectrum, we can tell the difference between those colors, right? Because there's a unique response associated with that. The detector does the same thing, except for it's able to quantify that, and it's because of the nature of how the data is collected, we're able to do there. So I'll kind of go through a video kind of showing that in a little bit more detail on the next slide. So we'll click on this real quick. So what we see is here is a blow-away of kind of what's going on inside the detector. You kind of have a series of main components with this. So what we see here is we're pulling the air through the orifice with we have a pre-burner. So what the pre-burner does is it helps flames from propagating. So in the event that you're using a high hydrocarbon environment or hydrocarbons are present, you're helping prevent that. So it's kind of like a silencer on a weapon on there. So again, we're pulling the materials through the device, we're exposing it to the flame. So the flame then what it does is it creates the exciting of those atoms. As soon as they relax, once they're out of the airstream, they produce visible light. So what we do is we collect that light. So we take some optics and we use it to focus it on a CMOS sensor. A CMOS sensor is helpful from the standpoint of it allows us to collect all the information on the visible spectrum, and then we're looking for the fingerprint associated with that. So it allows us to take something that is light, convert it into something that can be analyzed by a processor through the spectral response that's doing that. So you're taking light, converting it to electrical information or technical information, which electronics and a processor can do. And then we're looking for the spectrum of it. A couple of things with that. The amount of light is directly correlated to the amount of atoms that are present. It's a direct correlation of that. You also notice that there's no filters associated with it. So we're pulling the air directly from the outside, going all the way through the detector. So therefore, that's one of the reasons why this process is able to see aerosols. As long as the aerosols allow us to excite those atoms, we will then be able to see them because the spectral response is specific to each of those elements and that element only. So it's, again, because of the different classes of materials that you're seeing in this, which we'll talk a little bit more about, that we're able to delineate both the concentration and the presence of those elements with high degrees of certainty and as well as high correlation to the concentration. So therefore, it's a great tool to be able to utilize, because in the event of battery fires, you're wanting to make decisions fast about concentration levels, classes, and then the nature of the threat that's associated with those. So do I need to, if the levels are highly elevated, do I need to evacuate a room? Do I need to evacuate a floor? Do I need to evacuate a whole building? Do I need to evacuate a whole block? Those sort of things are helpful for understanding. And a lot of times these batteries are occurring out in, if they've gone exothermic, there's events outside in nature and winds change, and those prevailing winds can drive the threat profile to different areas. It's a way to help monitor and quickly decipher information associated with those. Go to the next slide, please. So pH paper, again, we're going to talk about those different tools. So first, flame spectrometry, now pH. So pH allows us to identify classes of materials associated with them. So in this case, we're doing acidic or alkaline type of materials associated with those. And those are associated with different types of chemistries of those batteries, and they have different correlations as part of the pH level associated with them. In some cases, it'll be better to wet those papers in order to help us collect that information more quickly, but the nature of the color of the response allows us to help understand that. Now, one of the threats, especially when you're dealing with battery response, and we're going to talk a little bit more about this, is understanding either the basic or the acidic nature of that. That becomes a threat to us as humans, for skins, other things, the caustic nature of that. So we have to respond properly with the right protective clothing in order to do that. But it's also help us to understand the nature of how these materials are behaving and what the nature of that threat is to us based on the pH. Next slide, please. Again, another delineation of them is F paper. So it's another great tool. It's super easy to basically be able to do. Now, what we recommend in this case is exposing that F paper to hydrochloric acid. So the hydrochloric acid, because a lot of times these materials, when they're coming, you'll be cutting in the airstream. By putting the hydrochloric acid, it allows that paper to pick it up very quickly and much easier, especially, again, going back to the thing that this can be an aerosol threat. If the paper is just sitting there dry, it's going to be a lot harder for it to pick up and to get a response. But by wetting it, it's allowing it to pick up those materials, especially those aerosols in the airstream, and then getting the response. So we're looking for the change in color of that, which will indicate the presence of the fluorides, which allows us to determine that. So it's probably with your LIBS batteries, but it's an important additional tool for us to help delineate classes of materials and the natures of the threats that are present. And then the fourth tool that we talked about, which is on the next slide, is your electrochemical cells with that. So they're very common. The interesting thing is these are actually operate similar to a battery. So there's electrolyte, there's an anode and a cathode with it. So for example, on an O2 sensor, oxygen enters the sensor through the capillary, which is on the left side of it. It's immediately reduced where it comes in contact with the cathode. It's reduced to hydroxyl, and the hydroxyl ions then diffuse through the membrane to the other side, and where they're produced to produce lead oxide. So the sensor is then picking up the presence of that voltage that's present because of the reaction that's occurring. So that allows us to determine concentration of those materials. Now, in the case of this, a lot of times we're using CO sensors to be able to be done. But in the case of dealing with batteries, you're really looking at the presence of the hydrogen. So one of the challenges with electrochemical cells, they are very fast responding, so they're cross-sensitive to a lot of different materials. So in the case of a battery type fire, what you're going to, a lot of times your CO sensor is a nice one to use, but it's really because it's telling you the information on the hydrogen ions. It's because it is cross-sensitive to it. So if your CO sensor is going off and you're dealing with a battery fire, it's giving you information on hydrogen and hydrogen concentration. So if you know the correlation factor on there, you can actually determine that. But it's another key tool for allowing us to giving us that information on the hydrogen, which is another key attribute of these materials and how to understand the response. So what we're just going to show you real quick is a real life example of sulfur dioxide. So what we're doing here is we have sulfur dioxide gas. We have a bunch of PIDs in there. So you can see the AP4C is hitting on the sulfur channel. So that's and the response is almost instantaneous. We have an IMS, which is on your lower hard. You see the pointing to the sulfur. There's almost an instantaneous response with that sulfur. Eventually, we're going to move that detector out because it's just going to constantly go to there. Now, your normal electrochemical cell will be sensitive to it, but it takes about 40 seconds for it to respond. So you're seeing we're putting the SO2 directly onto that sensor, and it'll eventually go off associated with it. Now, it's important to understand with every detector that you're dealing with is that you understand the response time. This doesn't mean that the detector is bad or not, but if it has a 40-second response time and you're holding it there 5 seconds, you don't see anything, and then you're using that to make an indication of what's occurring. The problem is it's there, it's just you haven't allowed the sensor long enough time to basically be able to do that. In other cases, we're showing you here some cross sensitivity on it. So some of these channels are set to different levels, and you can kind of see here again, by pumping it into there, we're eventually able to get an alarm on those cells associated with it. So it's just understanding your detector, what its limits of detection are, and then this response time becomes important with it. AP4C, because we're working on light, has some advantages because that's almost an instantaneous response. We're monitoring multiple times a second, giving you the output every 2 seconds. Electrochemical cells just take a little bit longer in some cases for them to respond to it. Next slide, please. So this is another good summary channel. So we'll turn over to Christina pretty quickly on there. But from the response of the different classes of materials, using the E cell, electrochemical cell, the pH paper, and your F paper allows us to delineate the presence of different materials that are in different chemistries, and allows us to delineate the different types of batteries that we're dealing with associated with that. In some cases, the response will be specific to them. So for example, if I'm getting hit on the arsenic channel, then that immediately lets me know that I'm dealing with a wet secondary lead acid battery. And we should also get a hit on the sulfur, and you also get a hit on the E cell because of the hydrogen aspect of it. So this is kind of a very helpful chart of letting you know what the reaction should be and what the reactions will be for different types of battery systems when you're dealing with it. The one that will be hard for us to delineate between, other than on the E cell, because the hydrogen is the nickel cadmium and nickel metal hydride, to identify between both of those. But those basically are still identifiable from the response on there. You want to continue on, Christina?
Yeah, and one of the things that we were looking at here was how can we take some of these tools and make them work for us? And so what we were looking at is that most departments have a CO sensor, pH paper, F paper, and many have an AP4C. So just using these, we can start to get a better picture of what we're coming up to. Now, there are other sensors out there coming along. I know we've used the infrared, gas-phase infrared from RedWave to actually see some of these things as well, which is pretty cool. So it's really going to be about the time, the access to the area, and what are we going to do from there. Now, why does all of this matter? First off, if we already have had the failure, it's often too late for us to even use this. But we want to characterize the toxicity, corrosivity, and flammability. So how do we figure out what the risk is to us? And then if we can determine what the battery type is, that oftentimes will inform response tactics, because as you can imagine, with different chemistries, we have to respond differently to most of the battery types. So one of the things we want to raise attention to, and we said right off in the very beginning with that first video, that white material coming out is not smoke, it's gases. And we have to remember that that gas plume is extremely toxic. Not to say that the smoke isn't toxic, because it is as well. But when we start looking at some of these materials that are coming out and look at the toxicities, whether it be the permissible exposure limit, the lowest level that we can be exposed to safely, or the immediately dangerous to life and health, where if you were exposed to this for a length of time, you wouldn't be able to save yourself. These levels are really important to us. Now, if you look down to these few that say milligrams per cubic meter, just remember that means that these materials are generally released as aerosols versus gases. And so they're coming out as liquids here, liquid droplets that are taking on the characteristics and flow movements of gases, but they retain their solvent properties as well. So just keeping that in mind, we have some materials here that are extremely toxic, but are at levels for arsine, hydrogen sulfide, that we can actually measure sulfur dioxide well below those levels using the AP4C. And then with our other tools, we're able to get a good round spectrum here. Now, what does this mean operationally? So for the alkaline batteries, there's really a low risk of fire with those. The problem that we have with those is always going to be about electrolyte leakage. And in that case, those ones have a hydroxide, so it's going to be a base. So we're just going to try to contain that electrolyte and neutralize it with a weak acid, something like citric acid. As I said in the very beginning, that was our first neutralization experiment when we were doing it with soda and using the acidity in soda to neutralize them. With a lithium metal battery, if it's a small battery, like we said earlier, and even the FAA is their requirement on planes is use a small amount of water and use up that available lithium. Now for larger batteries, you need to consider using a class D copper extinguisher. You can also use a graphite extinguisher, but if it's a large enough battery that it has vertical surfaces, then it won't stick well to that. So that's why we generally say the class D copper extinguisher. For the lead acid batteries, again, not as common for the fires there, but again, the electrolyte can be very problematic. The electrolyte in these is sulfuric acid. So you're going to use a base like sodium bicarbonate or sodium carbonate, whatever you have available for your bases to neutralize that electrolyte. Just remember that if you use the carbonates, you're going to have a lot of sputtering and splattering as the reaction creates a carbon dioxide as well as the heat of the reaction from the neutralization. If there is a fire, consider using dry chemicals. Even the water and foam will also work. You're just going to be spreading that material out further. And so something to consider. A lot of times when you have a lead acid battery starting to go wrong, it also, if it's a wet battery, could be that it needs to be watered. So if you start to see some of the lead acid batteries that we see in a lot of these battery farms, just remember that they often will have a water gauge on the side of them. And if that water gauge is showing low levels of water, they could be producing hydrogen sulfide gas at that time. You fill up the water and it may go back to operating properly with hydrogen and oxygen being released instead. With lithium ion batteries, we have to be a little bit more careful. The electrolytes in these are flammable materials, whereas the electrolytes in a lot of the other batteries were corrosive materials. So while we got rid of the corrosivity hazard, we now have a flammable hazard. And we've all seen what happens when that pressure gets built up in the battery vents with that flammable gas coming out into a flammable environment, and then we have jet fires coming out. If it is on fire, just remember that you might get a temporary knockdown from some of the dry chemical extinguishers, but they don't suppress the thermal runaway, nor do they suppress the flammable gas generation. So you will get that temporary shutdown, but those gases are still there. Remembering that you've got flammable toxic gases, sometimes you're better off to let things burn themselves out, depending upon the location. If it's not possible to let itself burn out, consider copious amounts of water for fire suppression, and you need copious amounts of water for that system cooling. And that system cooling is reducing the propagation and the spread. That's if it's on fire. If it's not on fire and you see a battery that is in early stages of problems where it's just venting, try to get that place into a vent the area to minimize the buildup of that flammable gas in the space. Now, just remember, as we start looking at these, the real issue when we're using detection isn't when it's about a fire. If you get a call to a place where there's a battery on fire, the last thing you're going to be doing is pulling out detection equipment. You're going to put the fire out in the best way that you can. But where we really see the detection coming in and where we've had to use it many times is suspicious odor calls. So if you get a suspicious odor call to a space and they have batteries in there, see if the batteries are off-gassing. And then look at the battery type and say, is this normal? Or is the battery having an abnormal off-gassing operation? And if so, then remove that battery. For CO alarms that are going off, and we've seen this so many times in homes, is that battery producing hydrogen gas? And if so, again, is it normal operation of the battery or is it abnormal operation? So we start looking at a sulfuric acid-based battery, that's normal, but it shouldn't be in an enclosed space. It needs to be vented. If it is a nickel metal hydride or nickel cadmium battery, then that's abnormal operation and something's wrong with that battery. It needs to be removed. So when we start looking at this, one of the issues when we first started playing around with this was from a call from a recycling facility where they had an issue where they were seeing arsenic in gas phase and they were seeing sulfur in gas phase. And they couldn't figure out why they were getting that. In reality it was a battery that was bad in the recycling facility. And so when they started going through and looking at mixed loads, we said, okay, is there a battery that's dripping? So if you have an electrolyte, an acid electrolyte that's dripping out and dropping onto a computer component below, because the computer components could have arsenic in the material circuitry and older electronic equipment, or is it just a battery that's bad and that battery is actually producing both the arsenic and the sulfurs? And in this case, it was a bad battery. So when we start getting issues with mixed loads of batteries, recycling facilities, collection points, these are the times where having the detection equipment there is really critical. Now, I also think of like when we start looking at collection points, you can look up online the collection points in your community where places like Best Buys or Home Depots or Lowe's or those types of places will accept back old used batteries so they get properly recycled. Well, the problem is they throw those all into a big bin and they don't really pay attention to the way that they are stored properly to ensure that they don't have any problems there at the collection point. And that's where we find that detection really plays a good role, is figuring out which one in that stack of batteries is the problem. And then, of course, we still have our fire events. So when we have a fire in a location, let's say it's even a home or in a garage, just remember that all of the batteries that are there that have been insulted by the heat of the fire are now potentially problematic. How do we quickly determine which one of those batteries are potentially problematic? Well, we can start measuring their off-gassing and say, is this normal off-gassing or is this abnormal off-gassing? And then start separating them out accordingly. When we have that battery on fire, just remember it's a bit too late to use your detection schemes. One of the things that I think it was Underwriters Laboratory did a fantastic study about some of the gases that were produced. And these were in the lithium ion batteries fires and it's with electric vehicles. And so what they were doing was saying, outside of that garage door, could you measure that it's actually the lithium ion batteries that are causing the problem, or is it a traditional fire? And the reality was no, you couldn't. You were actually, to get to those levels where you were measuring the material, you would have to be inside the garage. And frankly, not something that we suggest is that you go into that area where you have the fire and try to figure out at that point. Try to get the fire out first before you do anything else. And that just makes sense. Okay. So let's also remember that the chemistry and the science behind batteries is evolving rapidly, and it's only going to keep going faster and faster. So you must keep up with the scientific research to know what is coming into your community. This is going to be at a scale we haven't seen before because there's so much going on in this space. A lot of venture capital funds is coming in to work with companies and small businesses even that are developing those next battery chemistries. So understanding who in your area who is working on these is also very important. But the most important thing we can bring and try to drive home to everybody is when you start thinking about the fact that that material that is coming out of the batteries in the early phases are toxic and or flammable gases, please wear your proper respiratory protection and wear your proper dermal protection. So reality is, if you're from the fire side of the house, you should have your SCBA on and you should have your turnout gear on before you start working around in close to proximity to any batteries that could potentially be having a problem. That will minimize your exposure to the different materials. While you have all these materials that are not meant for turnout gear, we do have to remember that we also don't want to go into traditional chemical protective suits that aren't meant for fire environments. So we have to really balance our needs here. And what we find is in most cases, the turnout gear in SCBA is your best bet. We have seen time and time again where people say, oh, it's just a battery going bad, and they're going to move into a space. Just remember that a battery going bad could have significant amounts of HF gas in a small space, and that could mean long-term damage if you inhale any of that material. With that, Scott, do you want to talk about some of the upcoming webinars?
Yeah, absolutely. So what we try to do is have quarterly webinars of various topics that are hopefully interesting to people as you're dealing with it. So the next one we're going to actually talk about as we're getting close, unfortunately, to election season this year, and who knows what's going to happen with that. But talking about irritants, both commercial and homemade variants of that. And so we're going to talk a little bit more about those different classes and how to detect those. And then in December, we're going to talk about biological threats. So both the toxins that are present or purposeful biological agents that are more ones that are contagious or potentially shareable from the standpoint of that. We're going to talk a little bit more detail about that, as well as detection capabilities of that, which flame spectroscopy does have the ability to do that, and not many people know about it. So hopefully both of those are of interest to you, and hopefully this one was of interest. I do want to just add one additional comment to what Christina said, as well as if you're using the turnout gear. One additional aspect that the AP4C can help you with is just post-exposure, just making sure a lot of these, there could be an ongoing off-gassing concern with some of the chemicals that you're dealing with. So AP4C can always be used to just do that quick check post event response to make sure that your turnout gear is not absorbed some of that and off-gassing, just letting you know that that's cases, or just then you need to ventilate that further so you don't transfer the threats into other areas or onto yourself or to other people that cross-contaminate. So it's just another use of it as well.
I should have put that video in where we did that to show that we were able to measure it continuously. And it was really SO2 that we were doing to show that it does get into the gear and the gear holds it. It holds it really well. And then you've got to ventilate it with a fan or something of that nature, and then it releases it just as nicely. So just keep that in mind, that it's a good way to post contamination to say what the levels are, and then post decon to say, have we gotten it down low enough?
And that would also go to occupants that don't have the turnout gear, that it could get, obviously hooked on their skin or other things like that. It's another good indication for it, or use if you have to do decon, post decon, just to make sure that they aren't continuing to off gas or cross contaminate people.
Okay, with that, that was all we were going to show today. Hopefully this was fun for all of you to see our take on where the batteries are going. If you have questions on battery response, you can please email at any time. I was trying to do this a little bit differently than our regular battery classes, which are very focused on the tactics for suppression and focusing in on what are the things that we can do as a community to identify problems before they become a fire suppression issue. And that's kind of this take Scott and I had today, and we hope you enjoy that. We will follow up from this webinar with emails to each of you with access to this video as to that goes along with that. And so you should expect that over the next couple of weeks. And with that, I think we will say thank you, unless anybody has any specific questions. And if you do, please put them into that questions box on the bottom of your webinar, the GoToWebinar system.
Yeah,
right now, I don't have any showing up, so which is great. Okay, well, if you do have questions, please feel free to reach out to Scott and I, and we will get this video pulled together and set up for everybody as soon as possible. Thank you, stay safe, and have a great day.